In mathematics, this expression is oftentimes referred to as DeMorgans' first law. So what is it? Well, it means that the complement of the whole thing of A union B is equal to the complement of A intersections with the complement of B. Now, how can we know this is true? Let's first draw the diagrams and see if the diagram on the left-hand side is going to be the same as the diagram you get when you take and draw the set on the right-hand side. Okay, so starting off on the left-hand side, what do we want to draw? Well, first, let's have a look at what A union B is. A union B is going to be everything in A and everything in B. So you're going to want to highlight all of A and all of B. But then we want to take A union B and take the complement of the entire thing. What does it mean to take the complement of something? Well, it means to take everything that's not in it. So we want to take everything that's not going to be in A union B. So what is not in our shaded area? What is not shaded in orange here? Well, it's going to be everything outside of our two sets. It's going to be this whole region here. Okay, sometimes you'll see in math there's going to be actually a box to draw this like so, and there might be a U for being the universal set. So we're actually interested in this shaded part in blue. So what we should look for on the right-hand side is that we're not going to be interested in the two sets. Similarly, how here we're not interested in the orange part. Okay, what will we find? Okay, what is the complement of A? Well, the complement of A is everything that's not in A. So we can't shade anything that's going to be in our circle A. So we're not shading anything here. And then what about the complement of B? Well, the complement of B means nothing in B, so we're not going to shade anything with B. So what does the intersection mean? It means we want nothing in A and nothing that's going to be in B, which means we're not going to want to be interested in anything that's in A and B, so we're going to want to also similarly shade in the entire outside of our two sets. And here we find that they are going to in fact be equal. Okay, what if our two sets A and B don't have anything in common? Well, what is A union B going to be? It's going to be everything in A, so we're going to want to shade in all of A, and it's going to be everything in B, right? What about the complement of what we just shaded in? Well, it's going to be everything that we didn't shade in, and that's going to be the rest of the box. It's going to be the outside of the box. What about on the right-hand side? Well, the complement of A simply means we're not going to shade A in, and the complement of B simply means we're not going to shade B in. So what is left? Well, similarly, everything that's going to be left is going to be the outside of the two sets. So we find that the sets are also going to be equal in this case as well. You're going to find the exact same relationship whether you look at A being the subset of B or B being the subset of A, and you should go and see that for yourself. But now I think we have more than enough proof or more than enough reason to believe that this is true, so now we can start writing the formal proof for it. So let's remind ourselves that because this is going to be an equivalence, it means that in order to prove this statement is going to be true, we have to first prove everything on the left-hand side is going to in fact be on the right-hand side, or the left-hand side is a subset of the right-hand side. And similarly, everything on the right-hand side must be in the left-hand side, or the right-hand side must inversely be a subset of the left-hand side, like so. So we need to prove this is true, and then we need to prove this is true. So we have two cases to prove before we can conclude that this is going to be true. So let's go ahead and do that. Starting off, this is a for all proof because we're looking at any sets A and B, which means we're going to start with a let. We're going to say let A and B be sets. And now we can prove our first case. So our first case is going to be looking at proving the left-hand side is a subset of the right-hand side. What does it mean? It means we have to show every element on the left-hand side is also going to be an element of the set on the right-hand side. Or if we create an element X that will be any element in this set, if we can show that X can also be in this set, then because X is any element in this set and it's in that set, we can then conclude that this must then be a subset of that. So how are we going to do this? Well, first let's break apart what it means for X to be an element of our set on the left-hand side. Well, for X to be an element of the complement of A union B, it means that X is not an element of A union B. Okay, what does it mean for X to not be an element of A union B? Well, if it was an element of A union B, it means X is an A or X is in B. But for it to not meet this standard, it must be in neither, or not in A and not in B. So this means that X is not an element of A and X is not an element of B. And what do we know that, what does this look like? Well, this means that if X is not an element of A, then X is an element of A complement. If X is not an element of B, then X is going to be an element of B complement. And since it's an element of A complement and an element of B complement, that obviously means that we can say it's an element of the intersection between the A complement and the B complement. Fantastic. Okay, let's put this into actual words. So what is this going to look like? We're going to start by supposing our representative element, X. We're going to say suppose X is going to be an element of, open bracket, A union B, close bracket, complement. We can then say, then X is not an element of A union B. Fantastic. And then we can continue the sentence by saying, so X is not an element of A and X is not an element of B. Fantastic. Then we can say, if X is not an element of A, then X will be an element of A complement. And similarly, if X is not an element of B, then X must be an element of B complement. Now, given X is not an element, given that X is an element of A complement and an element of B complement, then X is going to be an element of A complement intersection B complement. Fantastic. So we've shown any element here is going to be an element of here. And because we've now shown this, we're going to conclude that, making A union B all complemented a subset of A complement intersection B complement. So there we go. We've proven our first case. Now let's go ahead and prove our second case. Okay, so for our second case, we're going to show the right-hand side as a subset of the left-hand side. And similarly to how we did it in the first case, we're going to show that if any element y is going to be an element of the right-hand side, if we can show that y is going to also be an element of the left-hand side, that's enough to show that any element on the right is an element of the left, which by definition makes the right a subset of the left. So how are we going to do this? Well, what does it mean for y to be an element of A complement intersection B complement? It means that y is an element of A complement and y is an element of B complement. What does it mean for y to be an element of A complement? Well, this simply means y is not an element of A. Okay, what does it mean for y to be an element of B complement? This means y is not an element of B. Okay, so we got our A and B that we needed to get. Now we need to somehow get the union. How do we get the union? Well, because we know that it's in neither of these, can we maybe get an or? I'm trying to think how you could possibly get an or here, because you need to get an or logic or some sort of or reasoning here in order to get the union sign. So how can we get that? I'm thinking we actually don't need to directly get an or. Obviously the and would carry down. Y is not an element of A and it's not an element of B. That's what it means for this to be true. These statements are the same. So we can say, since y is not an element of A and not an element of B, okay, so here's what I'm thinking. Since these two statements are equivalent, it means that the and must carry down here. And since y is not in A and it's not in B, then it can't be an element of A union B, because A union B means it has to be in one of those two. So yeah, if this statement is true, then it can't be in A or in B. So, and this can lead us to our conclusion. I think that's how this would work. Yes, I think that should be sufficient enough. If it's not, let me know down in the comments. So let's go ahead and write this down. So how's this going to look? We're going to suppose our representative element y. We're going to say, suppose there exists some element y in the set A complement intersection B complement. Fantastic. Then we can say y is an element of A complement and y is an element of B complement. Then we can say, so y is not in A and y is not in B. Then we can conclude, since y is not in A and y is not in B, then y would not be in A union B, so y is an element of A union B, and it's the complement of the whole of A union B. There we go, and now we can conclude that because this element is in the right and the left, it means the left is going to be a subset of the right. In this case, I'm talking about this. Obviously, it's the other way around. The right equation is a subset of the left is what that really means. So we can then say, therefore, A intersect B, the complement of A intersect with the complement of B, is a subset of open bracket A union B, the complement of open bracket A union B, close bracket. Fantastic. Okay, so now that we've proven both of the cases to be true, we can now conclude that since this is true and that is true, this must be true. So we can say, in conclusion, given A union B, all complement, is a subset of A complement intersection B complement, and A complement intersection B complement is a subset of the complement of A union B, then A union B, all complement, equals to A complement intersection B complement. So there we go. We've proven that DeMorgans' first law is in fact going to be true.